Hello everybody, I am Sci-Guy Geek, and we are going to be going over more EMag today. I'm going to be looking at the electric potential, deriving it, and going through some some problems. So, what we discovered last time was that the curl of any static electric field, any electric field for electrostatics is zero. That means that the field has no rotational component. And this holds for any static charge distribution whatsoever. Um, so because we have this static curl, we can uh, do some fancy things. So we are going to turn, using this knowledge of the electric field, we are going to be able to turn electrostatic vector problems solving for an electric field into an electric potential. Um, so back in section 1.62, we see that any vector whose curl is zero is equal to the gradient of some scalar. So we're going to show that in the concept of electrostatics. So, because the curl is zero, that means that there is no loop that you can make where the line integral will be non-zero. So, any closed loop that you make, no matter what the path is, the line integral is going to be zero when you come back to the point. And because of that, the value from A to B is the same for all paths. So if you go to A to B, then from B to A, it has to be the same as going from A to B in a different path, and then back to B to A in a different path. They both have to equal zero. Therefore, all of the paths have to be the same from A to B. And because of that, we are going to define some scalar function as the line integral from some reference point to some point R of the electric field dot dl. So the difference between these two potentials is equal to the difference between the point at potential B, so this equation, 221, for B, minus for A, so we have a double negative, which turns into a positive. So, this means that we go from the origin to B, and then from the origin to A, add the origin to A. But that's just the same, remember your calculus, as flipping, going from the negative from A to the origin. So, one is going from point A one is going from some origin to point B, from origin to point A, which is the same as going from A, the negative of A going to the origin. because A going to the origin is a negative, and you have another negative, and you get the same thing. So the final potential difference becomes just an integral from A to B of E dot dl, E along some path L. Now, we saw this back in chapter 1. The fundamental theorem of gradients states that this difference can be written as a gradient because the curl of E is 0. And that is the very important thing. This can be equated. So del cross E equals 0. Therefore, E equals some potential V. So we have that. So now we have the initial I'm missing a negative sign somewhere. Oh, we have, from the statement of gradients, we have this. So then we have, I jumped a loop. So then we have the fundamental statement of gradients just on its own is given here. And if we replace the difference by this fundamental theorem of gradients, then we have delta V, so del V dot dl from A to B is equal to the negative integral from A to B of E dot dl. But because this is true for any point A and B, you can take any path. Lucio, how you doing? Just going over vector potentials today. Not vector, just electric potentials. And we're just getting to the proof of why the electric field can be written as the gradient of some scalar V. So we have this fundamental theorem of gradients equaling this component. So we have E is equal to negative del V for any line integral. So let's go over this problem. K is a constant with the appropriate units for the possible potential using origin as a reference point. So let's look at we have E equals K times X, Y, X hat plus 2YZ Y hat plus 3XZ Z hat. So we want to see if this is a possible electric field. So doing good, just procrastinating? Hey, no worries about procrastinating. What are you procrastinating against? You've got some homework to do? Avoiding the Sunday scaries. So first thing we want to do is we want to see if this is valid. And this is valid if del cross E equals 0. So let's see what del cross E is. So if we del cross E is equal to the determinant of our x, y, z partial respect to x, partial respect to y, partial respect to z, and then we've got ex, e, y, e, z. So let's start eyeing this. So our first component is going to be partial with respect to y, ez. And we can see there is no y. So this term becomes 0. So we have 0 minus dz with respect to y. And this is going to have 2y component. Okay. X hat. So right off the bat, we know that this is not going to be a valid field. You have a test in the next few days. All right, what's the test on? Maybe we can, if we want, we can go over some problems. If you want some help. Depending, well, math or physics problems, I can help you out with that. So we have an x component, and right there, since we have an x component, we know that this cannot equal the gradient of some potential. So let's look at the other one, which is y squared 2xy plus z yz. So we have y squared 2xy plus z squared and 2yz. So first, partial y with respect to z is going to be equal to 2z minus z with respect to y. Z as a partial as a function of y, and we see that we have a negative 2z here. So the x component is 0. So we add, and remember we've got a cofactor here, so we don't do xz, we do zx first. Partial z with respect to x is 0 minus partial x with respect to z. There is no x here, so that's 0. Y hat and z hat. Z hat is xy, so this is equal to 2y yx minus 2y z hat. equals. General physics tests apply here in Brazil. We use our results to apply for the master's and doctorate degrees. Oh, nice. So what level of physics are you working on? Are you working on calculus-based physics? Are you working on just algebra-based physics? Are you going into stuff that you learn in college, or in America we have a high school, just general education. So we see that here, this field has a curl of 0. And there we go. So, you're just solving the previous tests. That's how I studied. That's how I went through everything. Again, if you want, we can go over some potential problems if you want to. How would you give them to me, though? You could join the Discord, and you could screenshot the problem if you want, or we can just kind of continue on with potentials. So the nice thing about the potential is it has to be in regards to some reference. So we know that this constant k is between a reference point and 0, but the difference in potentials doesn't matter where the origin goes. So no matter what reference point you pick, the difference between 2 points is going to have the same potential. And this obeys the superposition principle. So adding potentials common to some reference point is going to be equal to the adding of the individual potential. And this potential is in the unit of a volt, or a joule per coulomb. So 1 energy per coulomb of charge has the 1 unit of energy per unit of charge has a potential of 1 volt. So, we know from previous problems that the electric field for a sphere outside is 1 over 4 pi epsilon naught times the total charge of the sphere divided by r squared. The field inside is going to be, using Gauss's law, this is uniform spherical shell, surface charge. Big important thing. So if we do a point within the sphere, it encloses no charge. So therefore, Gauss's law says that it is 0. Therefore, there is no field. So we want to find points outside the sphere. We want to find the potential. So we write the potential is equal to E dot dl. And we simply have some path that we need to take. So let's take the path just from the origin directly to in the R direction. So we have this, and then integrating, we get Q over 4 pi epsilon naught divided by R. For potential inside the sphere, we have to break that integral into two pieces. So we have to break it from negative infinity to R, from infinity to R, and from capital R to some point R. So from the origin, that's why. Setting the reference point to infinity. I was wondering why they had to do two integrations. So you're setting the point at infinity, so you're going from the origin to the shell, and from the shell to the inside of the point. So you're enclosing no charge. So that's 0. Your field is 0. But your potential is not. Going from infinity to R, your potential is equal to a constant. All of these values are a constant. So just because you have no field doesn't mean you have no potential. It just means the gradient of your potential is 0. That means the rate of change has to be over the surface, needs to be 0. So we have gradient. The electric field is the gradient of some scalar potential, negative gradient of some scalar potential. So let's plug this into here and into here. So we have del dot del negative del dot V, which is equal to negative V squared. So from Gauss's law, we have Poisson's equation, del squared V is equal to negative rho over epsilon naught. And this reduces to Laplace's equation for areas with no charge. So this is our first partial differential equation, second order, that we can go over once we get into potentials. Next is the curl of a gradient, which is 0. This isn't surprising because the curl of a gradient is always 0. We actually used that idea to define the solution. So, if we have a localized charge distribution, we find that we have the same electric field as that of a sphere, just R is small. Setting our reference point at infinity, we have the potential of a single point charge is equal to the charge divided by a constant divided by R. potential of a point charge is just given here. And from the principle of superposition, we can sum up those point charges. But if we have some volume of charge, well, it's just the volume times the charge density over R. Corresponding electric field from this is given here, which we've had before. So, what we see is that the potential has no component vectors. This is purely a scalar problem. You are taking the charge density as a function of its position, dividing it by R, and summing over all of its volume components. So, uniformly charged spherical shell of radius R. So now we're going to solve using this equation. So if we find a point, law of cosines, we can describe this point as this here, r squared plus z squared minus 2rz cosine of theta. And then we get this messy integral. But note that there are no components, vector components. So we simplify this equation, pull out all the constants, which are the r squared and the sigma. And there's a 2 pi floating around here from the d phi component, because there's no phi component here. So, going from sine over constants minus cosine is given here. You can find that in the lookup table. And we get, plugging in our values, we get r sigma epsilon naught z on the outside, and r sigma over epsilon naught. In terms of r, total shell volume is 4 pi r squared sigma naught. So for r greater than the radius, we plug q over 4 pi r squared into sigma, and we get 1 over 4 pi epsilon naught q over r. And we get that q over capital R for the inside of the shell. So let's go over boundary conditions. Let's see, boundary conditions, and then I'll call it from there. So looking at Gauss's law, there are 3 fundamental quantities. We have charge distribution, the electric field, and the electric potential. And we can go from any one of these quantities to any other quantity using this triangle here. So if we have our charge distribution, we simply apply our potential equation for the potential, or we apply our electric field equation for the electric field. If we have our electric field, we calculate its divergence to get its charge distribution. We use Gauss's law. And if we have our potential, we can just take the gradient and find our potential, or we solve Poisson's equation. So now let's look at what happens to if there's a discontinuity on the surface. You see that E changes along a boundary with a charge distribution. So we're going to draw a Gaussian pillbox, which is just a rectangular prism around a surface. So if it has some surface charge sigma, then the volume integral is equal to the enclosed charge over epsilon naught, which is just the charge density per unit area times the area. And we pick A such that this is completely flat within that region. If you have some curvature, pick a smaller A. Now the sides contribute nothing to the flux. So we are left with the field above, the perpendicular field above minus the perpendicular field below is equal to 1 over sigma. The tangential component, though, is always continuous. Because if we apply E dot dl is 0 for a loop, we only have components parallel to the surface, and they are equal and opposite. And they are equal to that. We can solve the same for potentials. We can see that the potential is continuous across any boundary. As this path shrinks to 0, we just have the potential above equals the potential below. But the gradient is equal to the discontinuity in E. So, we had E parallel above is equal to E parallel below. So the tangential component to the surface are equal. So we have the full is equal to the normal component times the discontinuity factor sigma over epsilon naught. So we have that discontinuity factor and we have the potential difference. It's equal to that. And these are the boundary conditions to just above and just below. So, that's what I got today. Next up is going to be energy. And we'll take that up later. So I'm going to call it for today. Hope you all having a good time. Hope you all have a good Sunday. Take care. If you want more of this, please let me know. If you want more problem solving, we can go over that as well. So, take care everyone. Signing off.